Probably should wait to the end. So, good morning. I am going to talk about AI-assisted development, and I'm going to talk about two things. One is how we can use these techniques to solve problems ourselves, and then how we can apply it to helping us become more productive. So, the first thing I'm going to start out with is a definition, because I found that I kind of needed to come up with new terms. So I'm going to use this thing called trained function, and that means a function that uses a trained neural network to do some of its behavior. And if it isn't trained, I call it direct. It's kind of lame, but that's the best I could come up with. And then I also want to start talking by talking about the Church-Turing thesis, which is a hypothesis. It's a guess. It's a hypothesis, but one that's pretty widely accepted and believed. And what it says is that any algorithm can be simulated by a Turing machine. So a Turing machine is this concept that was created by Alan Turing about 100 years ago to formalize the notion of what an algorithm is. And then right around the same time, Alonzo Church came up with a different formalization of what an algorithm is called Lambda Calculus. And what they noticed was they both can describe the same algorithms. And so can a lot of other languages like Scala. So there's this notion of a Turing complete language is anything that you can write in a Turing machines, if you can write it in Scala, which you can, then Scala is Turing complete. But what that actually is saying is that there is a space of all possible algorithms or all possible functions. That's actually a thing. That's the Church-Turing thesis, what it's saying. So I actually quite like Lambda Calculus because it's a functional programming language and it's extremely simple. This is the whole grammar. There's no types, which is also quite freeing. It's untyped, so there's just terms. And a term can be one of three things: a variable, an application, or an abstraction. So a variable is usually named, like we name variables in Scala, but there's a notation, De Bruijn notation, that indexes them, so you don't have to deal with names. So I use that, but I start with 0, where they start with 1, but I start with 0. So a variable is a natural number, starting with 0. And an application is how you invoke a function. So normally in algebra or in Scala, we'll say f prints x to invoke f and pass x in. In Lambda Calculus, it's juxtaposition. So you'd say f space x. And so what I do is I always put a space between them, and I put parens around an application, and I don't put parens anywhere else in my notation. And the last thing is actually a function literal, or what we call lambdas. It's why we call them lambdas. It's lambda. Normally you have a parameter. There's just one parameter passed to a lambda in Lambda Calculus. So you name it. When you're doing indexes, you don't need to name it. So I just skip the parameter name. I say lambda dot, and the right-hand side of that is the body. And so the t there is a term. So where t shows up, it can be any of those three things, right? And that little tiny language allows us to describe any algorithm that can exist, any effectively calculable function. So that is an example down here at the bottom. If you can see the bottom, lambda dot in paren 0, 0, that's a lambda. That means it's a function. I can pass in a parameter. And what it's going to do is apply it to itself, and that's the result. So, okay. So that's Lambda Calculus. And what I wanted you to think about is this space of all possible functions. So I asked an artist friend of mine, an artificial artist that lets me have up to 15 free drawings a month, if it could help paint a picture of what the space of all possible functions might look like. And so what I'm imagining is that there's a space of all possible terms you can make in Lambda Calculus, and each term that's a closed function is a star in the space. So there is this notion of closed versus open, which also is in Scala. If you say f of x equals x plus more is a free variable, because I don't pass it in. I can only use that function if more is defined somewhere in lexical scope. That's an open function. It's got a free variable. A closed function is like f of x equals x plus 1. So the body x plus 1 only has one parameter, one variable, and it's passed in as a parameter to f. So that's a closed function. So what the stars are in this space is, I'm just looking off in one direction. They're the closed lambda abstractions in Lambda Calculus. And actually in this drawing, I have included all functions that anyone in human history have ever written. And it's this one right here. This is a little cluster of stars, this teeny tiny cluster of stars. I just wanted you to kind of appreciate that this is an infinite space of algorithms, and everything we've done is just this insignificant drop of the ocean so far. But what's interesting recently is that we've been discovering lambdas whose behavior is so sophisticated that people are calling them intelligent. And so even though we've been looking for intelligent life in the physical universe for a long time, the SETI project and whatnot, to my knowledge, we haven't found it yet. We point radio dishes at stars looking for radio signals, but we've actually found it in this space for some definition of intelligence. It's just the behavior is so sophisticated that people are calling it AI. So anyway, that's one visualization, but I have another one because I want to be more concrete. This is the artistic one. This is the programming one. What I did is I made a lambda, which is a star in this space. I found one that would generate all possible lambdas and assign them points in 3D space. So the way I do it is my algorithm over there on the left. It loops kind of through these three modes: variable mode, application mode, and abstraction mode. And so whenever it's in variable mode, and then it'll just loop again, variable mode and then application mode, abstraction mode. So variable mode, it always just emits one term. So the first time you're in variable mode, that's 0. And then the next time you're in a variable mode, it's 1. And the next time you're in a variable mode, it's 2, and so on forever, right? And then it'll just go to application mode. And what application mode does is look at all the terms that came before and pair them up in every combination that hasn't appeared before. So there's no duplicates. And then when that's done, we go to abstraction mode, and it just puts lambda dot in front of everything that came before that hasn't appeared before, so there's no duplicates, and then it repeats. So that, if you let it run forever, would generate all possible algorithms that exist, according to the Turing thesis, right? And then I had to assign the points in space. So the way I did that is I have natural numbers upper right here, 0, 1, 2, 3. I just make coordinates with natural numbers that sum up to the natural number that I'm at. So for 0, there's only one point that x plus y plus equals 0, so that's the first one. And then when 1, there's 3 points that sum up to 1, 0, 0, 1, 0, 1, 0, and 1, 0, 0. So that's the next 3 points. And then there's 5 that sum up to 2, and a bunch that sum up to 3 and 4, and so on. But that is, those are all positive x, y, and z. So because we're three-dimensional beings, and I'm doing this to help you visualize this space, I convert them to integers. So that's the lower algorithm down here. 0, 0, 1 is 1. But the natural number 2 is -1, and the natural number 3 is 2, and natural number 4 is -2. And it just hop back and forth like that. So I basically create the next term, create the next point, and then convert it to a point in 3D space that way. And so I'm going to show you what that looks like when you plot it. There we go. So this is looking towards the center of the universe. This universe has an origin, which is just the variable 0. So there's no star there. So the only thing I lit up as stars is closed abstractions, which are functions that you can call. If it's an open abstraction, it's dark. If it's an application, it's dark. If it's a variable, it's dark. And so you can kind of see a few clusters of stars in the center. That's the closed abstractions, the functions you can call after variable 0 and 1. And then there's a bunch of kind of dark space, which is mostly applications, because it's in application mode and it's generating more of them. And then there's this kind of wall of stars here, which is the abstractions for var2, essentially, that my algorithm generates after var2. So let's back up so you can kind of see what that looks like. So we're kind of at the edge of it. So that's what it looks like. It's an octahedron. It's an octahedron shape because of the way I assign it points. And it's got dark space in the inside because of the way I'm going through Lambda Calculus terms. But I thought that actually looked like something you'd see in an AI talk, so I thought that was appropriate. But I'm going to give you a little tour of a few, because these are all specific algorithms. So this one you have used before. This is the I-combinator. It's the closest algorithm to the center of the universe, of this universe of possible algorithms. And it is the constant function. So in Lambda Calculus, that's lambda x dot x. In Scala, it's f of x equals x. So we're up there. I don't know if you can see it very well. It says lambda dot 0. That is, in my syntax, the constant function. So let's go to k. The k combinator is over here. This one is lambda dot 1. which is a function that when you pass something into it, like let's say I pass 42 into this function, it's going to return a function that always returns 42. It ignores the input it gets and it returns 42. So that's how you get a constant function in Lambda Calculus. So that's a famous one. And then I've got a little omega one here. Omega combinator is a application. So it's not an abstraction. So I put a lambda dot in front of it. And basically, omega is an application that when you do reduce it, it gives back what it started with. So you reduce it again, it gives back what it started with. So it basically is the simplest infinite loop in Lambda Calculus. So if you if you ever forgot to increment I in your while loop, then you were here. And so I drew it black because that's a black hole. So there's some danger in this universe you got to watch out for. And then Y, you may have heard of Y combinator. That's right over here. He's kind of at the edge of this galaxy. And this is how we do recursion where we can stop when we're done in Lambda Calculus. So anyway, that's some famous ones. And what I did, this is kind of at the edge of this galaxy. So what's beyond it is, you can kind of see I'm at the edge here if I turn around here. What's beyond it is dark because I didn't render it. I did actually compute the next layer of algorithms, which is after var3, variable 3, and there's 42 million of them, which I didn't think was worth trying to figure out how to get that to fit in memory. But I did render the vertexes, just so you can see how big it is and get an idea. So I'm going to send you there, and then it takes a while to get there. So that just you can see it come up. That little tiny thing is the vertex of the top of the next octahedral galaxy out. And we're now traveling through space. It's kind of slow because it's space, so I'm going to come back to this. And we can look back and see how far away it is. But normally, like if I had rendered all the stars, this whole thing would be full of stars, which is like the next one out. Okay, so with that, I want to look at some different ways to implement stars. And this is a requirement spec, this little paragraph here, for a function named isPalNum. And isPalNum has a precondition. You pass it a string, and that string has to be length 10 exactly, and it has to contain only digit characters, 0 through 9. So if you fail to pass that kind of string in, it's going to blow up with an exception. Otherwise, it's going to return true if the number is palindromic, which means it reads the same forwards and backwards, and false otherwise. So like the example down here, 1, 2, 3, 4, 5, 5, 4, 3 through 1 reads the same forwards and backwards, so this function should return true. And then if I change that last 1 to a 9, then it's going to return false because it doesn't read the same forwards and backwards. Okay, so I created this helper function. This just checks the precondition. So if the string isn't valid, it throws an exception, and I'm going to use that from all my implementations. So this is the simplest implementation, I think. After you check the precondition, you check to see if s.reverse equals s. So that's one star in that space. This is one way to implement this requirements. Another way you could do it is just compare like the characters that should line up. I can just grab them and compare each one of those individually and end all that together. So that is an equal function. Given the same input, it will return the same output, but it's a different star. It's a different algorithm, right? So a different star in the space. So the next two stars for this algorithm that I want to, for this requirement spec that I want to do is do one that uses actual data and one that uses a model. So just to kind of mention what's the difference between actual data and model. This is actual data. It's a bunch of dots. I basically generated 100 points, and these are pairs of doubles. And so that's X and Y, and I just plotted them there. So that's 100 XY points. That's 200 doubles represented there. And what I want to do is make a model of it with this formula, f of x equals mx plus b, which is the formula for a line. So I want to find the best fit line for that data. And that looks like this. So I use linear regression. I use another lambda, an algorithm, to figure out how to minimize the mean squared error from the line to the actual data point. And so this is what it came up with. And what I wanted to point out about a model versus actual data is that actual data needed more. There's 200 points in actual data. There's just 2 here. And these are like knobs. Like you can think, if you go back to this formula here, mx plus b, I don't know what m is and what b is. I'm going to actually search for it. those are like two knobs where one all the way down is double dot min value and all the way up is double dot max value. And I'm asking this algorithm to like figure out like how to turn those to just the right place to minimize the error, right? There's two knobs. Okay, so then two differences. One is with actual data, I have 200 points, 200 doubles, which is a lot more data. And here I just have 2. But if I pass in an X that's in my actual data, I'm usually not going to get exactly the right answer. There's one blue dot right smack in the middle of the line, but everybody else is like near the line. So it's not correct. It's like an approximation, the model. But what's nice about the model is I can actually get approximation for any X. Like it can predict, like at this X that wasn't in my actual data, what's a likely Y. So anyway, that's data versus model. So I'm going to do data for sort of a data approach for is-palnum, because there's only 100,000 of them. Basically, if you take 5 digits, any 5 digits, and duplicate it and reverse one of them and put them together, that's a palindromic 10-digit number, right? So if you take 5 zeros and put a 1 in front of it, that's 100,000. So there's only 100,000 palindromic numbers with 10 digits. And I can fit that in memory, so I just stick it in a set of string here. That's the actual data, right? And then down here at the bottom, which is kind of hard to see probably, it just says is palnum equals pals.contains s. I just look it up and see if it's in there. So this is another equal function, but it's a different star in our universe of algorithms. It's a different algorithm. And this is one that actually looks at all, basically it knows the data. It's like the blue dots, right? So the next thing I want to do is a model. And for that, I'm going to use a neural network to make a model. And the first thing I'm going to do is take these 10 ASCII characters, subtract 0, the ASCII character for 0 from it to get an int, and then convert that to a double. So you can see over here, the second one from the right, I have an ASCII character for 2, and then I transform it into 2.0. And these 10 circles at the bottom are called features. That's what I'm going to feed into my neural network. Okay, so that's going to be the input. That's the first transformation this algorithm will do. And then I'm going to actually feed it into this. That's my architecture, chosen randomly by a friend of mine, an artificial friend. Essentially, those 10 green circles at the top are the input features. That's going to be my palindromic digits, kind of, as doubles. And then I have a row of 32 neurons. So it's kind of modeled after a brain, like neurons connected to each other. And there's 32 in the blue row, the blue layer. And then there's 16 in the kind of the lilac layer, and then there's 1 at the red. That's my output. And so the way it's connected is every neuron in each layer is connected to every neuron or every feature in the previous layer and every neuron in the one after it. So the top 10, there's 32 lines leaving each one of those because there's 32 neurons in the next layer. And there, in each of these blue ones, there's 10 leaving them to go back up to the green ones. And then down here, there's 16 leaving the blue, 32 entering the purple, the lilac. And then down at the bottom, there's 1 leaving each lilac one. And the guy down at the bottom, it has 16 coming. So that's basically it. And the idea with the way brains work is when stimulus comes in and it reaches a certain threshold, it fires out to the ones downstream, right? So the way you do that in math is with a formula like this. So this is my function template, like for the one I did earlier, it's like f of x equals mx plus b. So this is the one, the sort of the formula template for my model. And this one, the previous one had 2 knobs. This one has 897 knobs. I don't know what the right value is, but you can kind of see the colors here. I put them underlined. So x is a vector of 10, that's my input features. And so that goes in kind of in the middle there. And then I do a dot product with a matrix of weights. That's W1, and that's a 32 by 10 matrix because there's 10 coming in and there's 32 that I want to end up with because I need to come up with 32 outputs. And then I add a bias. So W1 and B1, W1 is 32 by 10 matrix, B1 is a 32 by 1 vector. And I just add them, and then I come up with a 32 by 1 vector, which is like my candidate outputs, except I want to process them one more time with this ReLU activation function, and that guy just gets rid of negatives. So you can see it down here. If it's a positive double, it will just, that's the answer. Otherwise, it's 0. And so that's the output of, that's a 32 by 1 output of this blue layer here. That's how I compute it. And then I'm going to do the same kind of process for the next layer. You multiply by a matrix of weights of the right, width and height, add a bias of the right length, and you get, I'm going to get 16 by 1 vector outputs for this this layer here. And that's what I feed into the next one. And there's the same kind of thing for that. It's getting smaller though. But what it comes out at the end is a different activation function. Sigmoid is going to give me a probability from 0.0 to 1.0. So what I want to train the neural network to do is, if it's a palindromic number, it'll be very close to 1.0. And if it thinks it isn't a palindromic number, it'll be very close to 0. So anyway, if you add up all those doubles, which is like the knobs that are going to be turned, there's 897 of them, which is a lot of knobs. And so if you take 2 to the 32, because these are floats, actually not doubles, is what I used, and take that to the power of 897, that's how many stars fit this, in the universe of algorithms, fit this formula, like formula template. And that's, I asked Scala Big Ant to tell me how many that was. That's how many stars I have to search through to find one that I like. That's a lot, right? So the machine learning algorithm, what it does is it starts out random. It has no idea where to start, so it just randomly starts. It just spins the 897 dials, and then it checks to see what's the mean squared error, or whatever your loss function is. It sees, well, how far off am I? And here the actual data is palindromic number and not palindromic number, right? And then it can go backwards in the neural network in that thing and figure out for each one of those knobs, to what extent does that affect the output and in which direction? And that can use that as hints into how to turn them. So it's not just blindly trying new things. It actually kind of figures out, probably the best direction is that way. And then it turns 897 knobs, pushes hyperspace, and goes to a different star in this space of stars. And it does that again and again, trying to minimize the loss. And when I did this, it took like 100 hops, and it was like very close to 0 loss, which was amazing, because I'm actually finding something in something, the size of the space is massive, and in 100 hops, it's able to get there. So what I wanted to kind of suggest is that machine learning is like star search. Basically, I'm looking for an algorithm. Because if I back up to this guy, this is an algorithm template, but like all these doubles, they're not free variables. What I'm looking for is a star where they're not free variables, that knows all 897 floats. It's actually floats in this case. So I'm looking through this universe of possible algorithms, trying to find one that is the best. And the other thought I had is that's also true of test-driven development. If you think about like the way you're supposed to do test-driven development is, first you write a test just for one little piece of behavior. And I use this. I think one of the ways that test-driven development is useful is that it helps you make progress on problems where you can't see where you're going. So like, is palnum, I know how to implement it. I mean, it's such a simple thing. I can just write, s equals s dot reverse. But a lot of problems, I actually can't see how I don't know how to do it. It's just too hard to see. But I can like say, well, if in this test case, I could do it this way, right? So I write a test, write it to make sure it fails. Then I go over here and I implement just enough code to make that pass. And that is a star. That's my first step. And then I go over here and I write another test, and I go into my function, I add just enough functionality to get that to pass. And that's a different star. And I do it again. I go hop to a different star. Hopefully it don't crash. But basically I'm hopping from star to star, kind of like machine learning, right? And I end up, eventually I hope that by the time I get to where I actually have to implement the thing, I have learned, to understand the problem domain a little better by going through this process. That's sort of the hope of TDD. And so I am training a neural network, but I'm training my own. In other words, I'm learning as I go hop, 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 hop. So I thought that was kind of, machine learning, is a little bit like the same process. Okay. So I'm going to show you 2 demos here. Well, One is, just so you can see this thing, this is the code for the, the neural network version of IsPalNum, and I've got Relu and Sigmoid. This is all pretty straightforward. Dot product. I've got some matrix things here. And this apply method is H. So that's H of X. And I've got some weights, which I'll show you in a little bit, but this is the apply method. And then I've got an IsPalNum prob that takes a string and converts, it does that conversion, to get it to 10 input features, and then it calls the neural network to get a probability back, and he returns the probability, and then all I do down here is I say, well, if that probability is greater than half, I'm going to call it palindromic. That's the implementation of this star. And so I can try it here. I say I'll show you IsPalNum prob 98765567889. That's a palindrome, so see how it comes back with a number very close to 1. And if I just change one of these, like let's change this to 8, it comes back with a number very close to 0. Right, so the first one will get turned to true, and the second one will get turned to false. So I did test this on all numbers that are palindromic. There's only 100,000 of them, and return true for all of those. And then I tested on a bunch of them that where it should return false for all of those. But there's 9,900,000 of those, so I didn't test it on all of them. So I actually haven't tested everything. And I want you to look at the weights. These are the weights. Whoops. There it is. So these are the doubles, the knobs. They're hard to see, but it doesn't really matter because essentially they're opaque. I can understand the other code, but I can understand this as a vector of doubles, but I have no idea why it does what it does. And just by looking at it, I would have no idea that it recognizes palindromic numbers. So if there's a bug that's reported, I can't say, oh, this shouldn't be 5.5372, it should be 5.5375 and fix it in the traditional way. I have to fine tune, I have to do more training, essentially. Whereas if in the direct part, these kind of functions, I can just see, oh, the bug's right here and I can fix it. So anyway, so that's the neural network version. And so then I want to go back to see where we are in our star journey. And just so you can see, this is a vertex of the next thing out. So I'm going to scoot around the side so you can see how tall this is. So this is just for variable 3. That's how thick it is. And if I go over here, you'll see another one off in the distance. That's another vertex. I just did stars that were within 1 or 2 distance from the vertex. I rendered those and none of the rest. So in between these two things is full of stars for that galaxy. And then if you look down here, this is where we came from. You can see it. That's how far away it is. And everything in between here and there is applications that were generated by application mode. So this space basically it's just an infinite series of octahedral shaped galaxies of stars that goes on forever. That's the space in which you work every day as programmers. Because basically the metaphor is that when you write a function, you visit the star. You found that one. Okay. So now let's talk about when to use this as a tool. I wanted to ask you if you think the neural network version is correct. I told you about how I tested it. I have a good feeling about it. I think it probably works. But with trained functions, I think we don't really write them. We raise them. We try to teach them right from wrong. In this case, palindrome from not. And then we send them out in the world and hope they don't disappoint us. And if they do disappoint us and there's a bug report, we can't fix it in the traditional way. We have to feed it new data. And, it's really tricky to figure out. It actually took me 3 tries to get the data right for this thing. Because it kept telling me that something was almost palindromic. Like if I had everything palindromic except 1 was off, it would say, well, that's 0.8 palindromic, which is possibly what I would want, but it's not what I wanted. I wanted it to be all the way down to 0. So the obvious, it should be obvious, conclusion from this is that we shouldn't use these unless by default, we should use them when we have a specific, when we can't do the other way, which I call direct. And I tried to think about how to say this. And the first thing I thought of was, if I don't know how to implement the thing directly, then you should use, a neural network. But a lot of times I don't know how to implement it to start with. So I came up with specify. If I can specify its behavior, then I should try to implement it directly. So for example, I can specify I can specify the is_num function. That's easy for me to specify. I can't specify a function that recognizes cats in pictures. I don't know how to specify that formally. I can get a bunch of people to say that has a cat in it, that doesn't have a cat in it, and then I got data, and then I can train. But I don't know how to describe it. So the reason I wanted to say that is because I've seen like some things that people are doing with AI to apply to make development for productivity kind of may fall into this category. So one thing I don't know how to do is I don't know how to specify, if given some text that describes a function, return some text that is the function. So that's a good use for a neural network. So this is, I just pasted that requirement spec from the slide into ChatGPT, and it wrote it for me. So it also then described it. So this is kind of like text to code and code to text. So that's two tools that I think are really, especially the first one, text to code, is very helpful to our productivity because we can get a lot of stuff done for it, a lot of things done for us more quickly. It doesn't get it right a lot, so you still need to know what you're doing for the time being, a human. But I think text to code is very powerful. This guy is public, so you shouldn't put anything in there that is confidential. But I imagine that people will have private large language models they can do this kind of thing in with their own, code. So that's a big one. Code to text, I think, is a little less useful because I can read the code almost as better, maybe even better than the text that describes it. But if you really can't understand something, you can paste it in there and see what it says. And I think there's a little bit of rubber ducking aspect to chat bots. There's the notion of I think it was a Pragmatic Programmer book that mentioned that to help them figure out a problem that they were finding a hard time figuring out, they would put a rubber duck on the desk and then explain it to the rubber duck, and that would actually help them figure out what was going on. And it may have been just an excuse to talk to themselves. If someone comes up and says, "Are you talking to yourself?" He'd say, "Well, I'm talking to the rubber duck, obviously." So I think this is kind of like a smart rubber duck, or it talks back, and it can help you figure out things that way too. But another one that I think is natural that works today is code completion. We've been using code completion to finish method names forever, and now it just gets a little smarter. So here I typed in a test name, and it gave me the test body. And the one this one is GitHub Copilot. I thought it was the best so far, but it's again, that goes out on the internet. So if you're not supposed to be revealing what you're working on, then you can't use this one. But I just think that's a natural kind of way to integrate it. It's like cruise control got smarter when it could tell how far you were from the car in front of you, and that just made it better. And this is kind of like making code completion better, I think. And for Copilot, I feel like it gets it wrong a lot, which is annoying, but it gets it right enough that it's, for me, worth it. But you have to try it. So that's two ways of doing text to code. So the other two combos here is text to text and code to code. And text to text, I think, is really useful too. So this is, using an LLM to just ask about the stuff that you're working on, like how does this function work? Like I could paste in the h of x and say, what's it doing? And it could explain it to me. Or ask about, domains, stuff that's not like specific to your company, but specific to, some topic. Like you can go to Wikipedia and get a whole wall of detail. But this is like you ask a question, you get a little bit of answer, then you can drill down and get a little bit more. It's just a really nice way to access human knowledge, I think. So that's text to text. So I think that's another one. The code to code one is the one where I want to, I think that's where it kind of falls in the category of, can we write a direct function? So the example there I want to give is a pretty neat product. It's only available for Java. It's called DiffBlue. This company's called DiffBlue. And they do reinforcement learning. They don't use a large language model, and they'll generate tests from your project. So if you got a project that has integration tests but no unit tests, you can just run this thing overnight and it'll just generate unit tests. But what they're doing is they're generating unit tests from the actual code. So it's not tests of correctness, it's tests of what it's doing. So if you fix a bug, it will fail a test, right? So it's a regression test. So what's missing is it's hard to know what the intent of the programmer was, so it doesn't care, it just generates a test. But it doesn't use an LLM. What they do is they actually you have like a little private neural network for your project, and it's trained on how to write tests, for Java. And then, so you ask it to go do that, and it figures out what sort of to do in what order by analyzing your project. And one of the things it'll do is look at code coverage, right? Because they're trying to flesh out your code coverage. So then they say, okay, let's write a test for this function, and they try it. And if it doesn't compile, that's fed back to the neural network, and it'll learn in other words, they use that feedback to train it right there. So it's going to, over time, learn about your project. So it'll try a few different ways, and it gets one to compile. It may be that it was using something from your project wrongly, and now it's learned how to use that from your project, right? And then they'll try to run the test. Well, if it fails, that's a problem, right? So it goes back and it tries to get that test to pass. Then it'll look at code coverage. It'll actually get the code coverage I was aiming for. And if I didn't, then I'm going to throw that one away and try again, right? And over time, it's not only sort of fleshing out your test coverage, it's also learning about your project privately, right? So I think that's going to be a powerful way to do things, is we'll have private things. Your company will have a large language model that you can ask questions of. Your laptop may have a neural network that's kind of learning about whatever it is you're doing and help you do it. But the question I would have, again, is I would apply that, do we know how to write a direct function to convert code to code? Because the Scala compiler converts code to code, right? Converts Scala source code to bytecodes. It doesn't use AI. So what I think is missing, it's called the Oracle problem, is we don't know what the intent is. Like if you look at a bunch of code, I can generate tests that are regression tests that will fail if you change something, but I can't generate tests that actually test it for correctness, because I don't know what your intent was for correctness to be. So what I was thinking is that the way you could define correctness, like what your intent is, formally, is with a statement of predicate logic. So instead of maybe writing a test first, if I could write a spec first, where it's of this shape, where it's like for all x, p of x implies q of x. So for is_num, for example, p of x is the precondition predicate. That's the length has to be 10, and every character has to be a digit. And then q of x, you'd call the function, and then assert something about the output. So here I'm calling is_num, and I say, well, that is going to return a Boolean, and it has to be equal to this Boolean, which is x equals x sub reverse. No matter which implementation, which of those 4 stars I showed you, one of them was identical to this x equals x sub reverse, but given this, then I know actually what is the requirements, and I should be able to generate actual tests against the requirements. And maybe you never need to write them, because can you just generate them? So you write this. And so what a human would need to write would be specifications. That was sort of my thought when I saw the reinforcement learning thing. I thought that's a great technique, but do we really need to use AI for code to code? So anyway, that was my question. So the last thing I wanted to do was I just was curious to hear what people think about this. It's what do you think is useful for your job, like what would actually be practical and what is not, so you can tell me now or during Q&A, or you can come up to me afterwards and just tell me. I'm just curious what people think. To what extent is it hype? To what extent is it a fad? I don't think it's a fad, but that was my question. So that is all I got. So I got 5 minutes for questions, but while we do that, I think we should go back to. I'm lost in space here. Oh, this isn't space, that's why. anyway, yeah, you can. Anybody have a question? I'm going to. Yes.